because of this question.
I don't know. Actually, I just read the same piece here. I just see it. I haven't seen
Okay, so last time we stopped at the quantization argument, and we said that one of the things we need is a gap for the excitations in the bulk. Now, in the case of the integer effect, it's actually simple to explain a gap. Because if you remember, the energy levels for the Landau bands, they depend on this index n of the Landau band. And we have actually two indices, m, which label the orbitals, and n that label the Landau level. So there were a lot of states for each n. Let's say n equals 0. So there was some energy, h bar omega c divided by 2. Then there was another band for n equals 1. And if you fill all the states, and remember, m maximum, the maximum number of orbitals that you could fill, it was just given by the number of flux quanta that you could fit in the area. So it was V times the area of the sample divided by the flux number of flux by the flux quanta, and that tells you the number of flux quanta that you can fit in the area A. So in the case of the integer effect, remember that the feeding fraction nu was equal to the number of electrons divided by the number of flux quanta. When the number of electrons is equal to the number of flux quanta that you have in the sample, you basically, for each of these levels, you put one electron, you fill completely the first Landau level. Now if you want to add one more electron, you have to pay this energy gap, h bar omega c. That's the energy cost to put one more. So here's the gap. We have a gap for the excitation spectrum. Now, in the case of the fractional effect, if you just redraw that figure, but now let's say that n equals a third, so that we're down to the first Landau level. We're just going to fill 1/3 of these states in the lowest level. And let's see, well, all these states have the same energy. Well, I could choose to fill this one, and out of 6 levels I fill 2, that's 1/3. Oh, but there are many ways that I can fill all these levels. For example, in this case, if I have 6 choose 2, there will be 6 choose 2 possibilities of writing state by occupying 2 levels. So you can see that there's a massive degeneracy here, if I just consider the kinetic energy. And all these states here are going to be n equals 1. So how do we explain a gap? Because if anything, we have this massive number of ways of filling up 1/3 of these levels. So you cannot explain any gap at fractional filling unless you take into account electron interactions. So one of the things that we're going to show now is that, well, actually we just argued it, but we need more to explain a gap. We need electron-electron interactions. And if there is a gap, you can already guess the order of magnitude of the energy of this gap. And it will not have to do with the h bar omega c. It will have to do with the energy scale, the characteristic energy scale of the problem, which is E squared, the Coulomb energy, E squared divided by the characteristic length scale. And do you guys remember what's the characteristic length scale in this problem?
Magnetic length.
Magnetic length. So it's LV. Well, there should be some absolute here, some dielectric constant for gallium arsenide, and some number of order 1. Okay, now let's go back to our wave functions. And so far, I wrote only the single particle wave functions. Now let's talk about many body wave functions. Because for one of the things we're going to see here is that since all these single particle states have the same energy, and we have this massive degeneracy, this is a very complicated problem. It's one that you cannot deal with in perturbation theory because this is no perturbation. Any interaction, since you still have no, it's different in the case of the Schoenberg discussed that you have a Fermi surface that, in this case, you quench kinetic energy, and all these levels have exactly the same energy. Yes?
The question about the length scale. You have another length scale, which is the average spacing of the electrons.
Right.
Why don't you use the average spacing instead of the length for the...
Okay.
For the
Actually, these will be equivalent because the average spacing between the electrons. Remember, the filling fractions, for example, if it's 1/3, there is a relation between the average spacing and L0, which is a function of the filling fraction. So these two are going to be the same order. Yes?
Is there a bound for this energy compared to the inter-level excitation energy?
Oh, the Landau level spacing?
Yeah.
Okay.
Is there a bound?
You can actually calculate, see, they don't scale in the same way. This one is linear in B, right? The higher the B, the larger this spacing. Remember, LB squared goes as 1 over B, right? So L goes as 1 over square root of B. So this energy scales as a square root of the magnetic field. So for a large magnetic field, this spacing is always going to be much larger than this gap, which is actually good for what I'm going to say next. We're going to project everybody down to the first Landau level. We're going to forget about the higher Landau levels. But this is the point that I want to start making here.
Question.
Yes?
So in case of the electric one of all of it, the our electrons that will interact. So they also you need them to fill the gap and all. Are they completely uncooperative?
No, they will be. No, they come in. One of the things that, the most naive case is that, if you fill this up, now you can treat the electron-electron interaction as a perturbation, okay? And they should renormalize the ground state energy. They're going to have an effect in the excitations, but they won't change the fact that these are field states. Okay? So let's go back to our wave functions, and I'm going to take them only at the first Landau level for different m's, and I'm going to write this as some normalization factor. If you go back to the wave function, the generic wave functions that we wrote, if you set n equals 0, you obtain something of this form. Now let's ask the question of how to write the many body wave function. Even for nu equals 1. Okay, we have all those orbitals and we have to put one particle in each orbit. But these are fermions, so we have to anti-symmetrize the wave function. Well, we know how to do that. We can write a Slater determinant. So, what you write is that the main body wave function for nu equals 1 would be equal to, I'm going to forget this factor in many places because, see, this factor is common to all wave functions. If I'm going to multiply a bunch of these single particle wave functions, there's going to be one for z1 magnitude square, z2 magnitude square. I can just take all those factors outside. These ones are the ones that are different for each level that you're going to fill. These are the same Gaussian, irrespective of m. So if I do that, if I just leave those guys aside, I can then fill out the states from n equals 0 to some maximum m. If I have n minus 1, if I have n particles, that's what I would do. Particle number 2, I'll do the same thing. All the way down to particle n. And I have to compute this determinant. Okay, in my days in Brazil, we used to learn how to compute that determinant in high school. So I know that. I learned it here. Okay? And it's the van der Waals determinant. So this wave function in any body problem is can be written as product I less than j of zi minus zj. And it's the van der Waals determinant. Now, one thing that one should notice is that, well, we know this is an anti-symmetric function if I exchange any two particles, zi, zj. For that we can see for two reasons. One is by construction. This is a Slater determinant. Another one is, well, you take this and you just exchange two particles and you see that you're going to pick up a minus sign. There is going to be one term, which is the zi minus zj, for the two particles that you're going to exchange. That one will flip sign. But there are other terms that will flip sign as you exchange zi and zj, because there are the zi's minus zk's. But you can work it out and see that you always pick up a minus sign. So this is a wave function for the nu equals 1. So then comes the question, how do you write a many-body wave function for nu equals 1/3? And that's when really that's the strike of genius of Laughlin, how to do it. So let me write down the answer and make arguments for it. So let me call psi 3, this stands for nu equals 1/3. Well, you raise that to the power 3. Now you can see that that's going to pick up a minus sign if you exchange two particles. Right? Because this is basically, this wave function raised to the power 3. So if this one is odd, if you exchange two particles, this one will also be odd. Now, why would that be the ground state of the nu equals 1/3 state? Well, Not just because it's anti-symmetric, right? That's a condition, because if you want to write the wave function for many fermi, we need that. But then, let me give you a few reasons, okay? We cannot go into too much detail. One is that you can take that as a variational wave function. By the way, if you're going to actually plug in and compute an expectation value of your energy, when you add to your Hamiltonian the electron-electron interactions, right? So you have to take that wave function, but also put in the another term in the Hamiltonian, which includes the electron-electron interactions. And you can use that as a variational wave function and see what you get. And then you can compare in a small system. You can diagonalize it exactly, and you can compare. So that's what Laughlin did. Okay? But then, as there's more and more work on the problem, one can actually show that there are some potentials, not the Coulomb potential, but some short-range potential, the double derivative of a delta function, for example. If you have that as the interaction between particles, this wave function is actually an exact eigenstate of that Hamiltonian. And so in numerical diagonalizations of small systems, support the fact that this wave function captures the right correlations between the electrons. Yes?
And even if you have a short-range potential, so isn't it surprising that the wave function that you write down does not depend at all on the coupling that you put in?
Well, given a certain potential, it's not surprising that it will depend on the coupling, because since you start with the degenerate levels, the coupling just tells you the scale of the gap. But the type of interaction should change the wave function. Okay, you shouldn't expect this wave function to be exact for all potentials, and it's not. You will have a large overlap. But what it does physically is that, you see that Zi minus Zj cubed? See, if you bring two particles, I and j, close to one another, the wave function vanishes. So it's capturing the fact that the repulsion wants to keep these particles far apart. And it wants to keep them with a certain relative angular momentum, okay, which is the 3 coming here. So as long as you have some potential that wants to keep them apart, they're going to start going around each other in that form. Yes?
Why did you call it an electron gas?
Don't call that an electron.
Yeah, in the first lecture you said this is an...
Oh, two-dimensional electron gas?
Why is it called an electron gas?
Okay. At that point, I hadn't put any interactions, right? Remember when I saw for the Lambda level, when I saw for these wave functions, I had no interactions. So this was a gas of non-interacting electrons. And it was two-dimensional because we made the sandwich, and we quenched the motion in the z direction so that they could only move in the plane. So there was two-dimensional, and it was an electron gas because at that point we had no interactions. Now,
in reality, it's not.
It's not a gas, yeah. But in reality, actually, that's why we just needed to turn on the electron-electron interactions to start talking about the fractional effect. But suppose that you had no magnetic field. If you actually had no magnetic field, there would be still some residual electron-electron interactions. And you could think that this would actually be depending on the density, so that you have a semiconductor while you're making the effective mass approximation, right? When whatever mass we wrote there, it's not the mass of the electron, it's m star, the effective mass in this semiconductor heterostructure. You could think that this is actually the realization of the 2D Fermi system that Shankar was talking about. Because we have an effective mass, we would have like some Fermi surface at zero field. Fermi surface, and there would be some electron-electron interaction. So it would not be the gas, but it would be the liquid. And talking about liquid, yes?
Is there a handwriting way to understand why it's 1/1 U which is sitting in the power? Is there some kind of symmetry?
The filling. the filling fraction. It's actually, if I write down this wave function for, say, odd integer denominator, because actually you see that the filling fraction was the fractional Hall effect is more robust for filling fractions like 1/3, 1/5, and then this number, the inverse appears here.
Yeah.
Now, that number appears there. It's the inverse of the filling fraction. There's a simple reason, and it's the following. See, when we got the nu equals 1, we just took n max when you fill out all the orbitals, and we build this later determinant. When you raise this to the power cube, effectively what you're doing, think about, suppose you expand this wave function here as a multinomial. Then you just go there and count all the powers of z's, and that's going to give you your total angular momentum. It's going to, you can actually relate in particular, for example, when I expand this guy, say for example, I take particle 1 at orbital 0, particle 2 at orbital 1, that's going to be one of the terms that's going to come out of that expansion. When you raise this to the power cube, and you look at the orbitals, you expand the area by a factor of, the area has to be expanded by a factor of 3 because the filling fraction is going to go down by 1/3. So that would be the simple reason. So if you just count the effective size of this, it's 3 times bigger. If you put 5, it's 5 times bigger. Okay. And you have the same number of electrons, but the area got bigger. Okay, so you have more fluxons fit in that area. So you have more fluxons and the same number of electrons. Okay, so I wanted to say here that, actually I mentioned liquid, right? This is actually, we call this a liquid state because there's no broken translational symmetry. For example, this is not a charge density wave, it is a liquid. There is some kind of order in this liquid, but it's not associated with symmetry breaking. Hopefully I'm going to have some chance to talk about it. It's Wend's notion of topological order. What can I say about the numerical diagonalization? There are a couple of things that you can look. First, that indeed, if you plug in this wave function, there's a gap that separates it from, if you do exact diagonalization of the system, with the Coulomb interaction, there's a gap. And the overlap of the ground state that you find for the few particle system and Laughlin's wave function, we get a pretty large overlap. Overlap of, I think for the time was like 6 particles. Now I can do, have much bigger computers. So you get overlap of 98%. And again, because even if you, there are potentials for which that overlap is 1, because that's the exact eigenstate, like double derivative of the delta function. But this wave function is capturing the right repulsion that 2 particles want to sit together. Okay. Now, let me start discussing some very interesting properties of that state. For one, you could ask, okay, that's the ground state, but what are the excited states? And I'm going to argue that the excited states of this 1/3 state actually contain quasi-particles that have fractional charge. So let's start discussing.
I have a question. It's also commonly called an incompressible liquid. What is that?
An incompressible state, yeah. Incompressibility here comes because of, if you want to create an excitation, you have to, for example, you want to add something in the bulk, you have to pay this energy gap. So you cannot create a density fluctuation without paying an
So
energy.
incompressibility just means there's a gap in the spectrum.
Density.
Then to create a density fluctuation, it takes, because well, in the bulk, actually we'll see that on the edges you can always make a density fluctuation without paying any energy. But in the bulk, you have to pay the energy gap to create any disturbance on this density.
Maybe another way to say it is that in a compressible fluid, you can change the density uniformly by 1/1,000,000 of a percent. The whole liquid, you can change it a lot in small regions of carbon, every atoms, and they will be the quasi-particles.
Right. You can even see, even in the case of the integer effect, that if you want to put one more particle, you have to fill in an orbital, right? If you just want to put one more particle anywhere in the system, you're going to have to put in the next Landau level. So that it's easier to understand in the integer case. And like Shankar said, if you want to change continuously the density, well, how can you change continuously the density, say, in the integer effect, where you're adding more particles? But it doesn't matter how you do, you're going to have to start occupying that extra Landau level. Even to put one more, imagine filling it up continuously. Okay, so let's make the case that there are fractionally charged excitations. So, let me first argue the following. Remember last time when we inserted the flux quantum to a geometry that had a hole? If you go back to those single particle wave functions, and you take the plane, or let's take our circle, we work on the circular system, and you put one more flux quantum at the origin. That has the effect, if you insert one flux quantum, you take your Hamiltonian, at the end of the day, you take your Hamiltonian to exactly the same Hamiltonian as before. And if you did it adiabatically, you take an eigenstate to another eigenstate. In this case, remember that the larger the m, the outermost is the orbit. And the m basically counts the number of flux quantum that you have inside that region. If you insert one more, you push your orbit out. So the effect of the insertion of one flux quantum is to take that Zm to Zm plus 1. It's like a shift register. You take whatever state, you have a Zm, that wave function goes to the Zm plus 1. So this is for one orbit. That state from M gets pushed out to n plus 1. So if you had one electron sitting here, that electron at the end of the day is going to be sitting in the next orbital over. So we could ask, what happens if you take a 1/3 state and do this exercise? Put through one flux quantum. Well, you're going to be pushing all the wave function, all the z to the power m. If you expand this wave function, there's going to be z1, z2, etc., and they're going to be raised to some power m. You're pushing all of them out by one orbital. Well, that can be done if you take this psi 3. You're going to go to psi 3. Let me call this psi 3 plus of z1, etc., zn, which is going to be equal to the product for all i's of zi times the psi 3 wave function. I may need to change the normalization, but I'm not going to worry about it. So see, what this factor does is say, when I expand this wave function, for any m in any of the terms, I'm just going to push that m by 1 over outside. And this does the job, right? Because I get a power of zi, so that's pushing all of the particles one orbital over. I'm going to rewrite this just more generic. That's because I did it at the origin. If I had put my flux somewhere else, some position, let me call this Z0, that factor would be the position of the insertion. And since we did this insertion of the flux adiabatically, we know that we would go from this ground state to an excited state. So this is an excited state of the 1/3 state. Now I'm going to have 3 different arguments of why that has charge that is fractional.
Here you assume that the Hamiltonian of the system in the fractional one-fourth plateau is the same as the Hamiltonian of the integer one-fourth state.
What do you mean?
Don't you make the analogy, as far as make the analogy with the regular orbit of the fourth plateau.
Oh, no, but this argument is actually independent of any Hamiltonian. That's a gauge argument that by inserting that flux, I'm just looking at okay, those are the wave functions for the non-interacting problem.
Yeah.
So think about usually what is it that does? It gives us some single particle basis. And then you're going to have to go and write your many-body states, like for example, you construct your Fox space. But all we say here is that those states, they have the effect in the single particle states to shift them 1 over. How are you going to paste together many single particle states to build your many-body state? That will depend on the Hamiltonian. But what I'm saying is that if you take whatever Hamiltonian, whatever wave function, by applying one flux quantum, you have that effect. That you're going to shift, as long as you're sitting down only the first number level, that you're going to shift all of your orbitals, all your, whatever way you combine all those many-body, all those single particle states to make your many-body wave function, how you decide to occupy your different angular momentum states. And that will depend on your Hamiltonian. But whatever way you decided to do, by putting one flux quantum, you're going to shift them all over. Okay, so the first argument is, if I'm shifting everybody down, or up or out, by 1, so I get, at the end of the day, see, I had this outermost orbital, and that guy got kicked out, so we had this flat round table. At the end of the day, you put a flux to the center, and that last guy fell out and got pushed out. So you have your n max, and your m max went to m max plus 1. Okay, the first argument is the least rigorous, but it's to give you some intuition. The Fitting fraction tells you the number of electrons per number of flux quanta. And the number of flux quanta is basically the number of orbitals that you fit in that round table. if you pushed one over and you say, now that I have 1/3 filling, that means that you have one electron being shared by 3 orbitals. If you picked one orbital out of the table, okay, if you push that one out, of course there's going to be a new one coming in the center. But one electron is sitting, it's shared by 3 orbitals. You kick one orbital out, so you kicked 1/3 of an electron out. So the charge that went out is equal to E over 3, but well, the orbital went out, but now think that you have a an infinite table, or you're just pushing that charge out to infinity. But you didn't change the number of electrons in your system. So something has to compensate. That means that in the center, when you push them out, you left that z to the n equals 0 orbital there in the middle. And that creates a hole. That one is not filled. So this means that there has to be charge Q equals minus E over 3 to compensate for this. So you push E over 3 out, leaving minus E over 3 behind, in such a way that you have the same total charge as before. Okay. But
how do you know it's all sitting in the origin? Maybe it's spread out over the whole disk.
how do I know that that is sitting near the origin? Because, well, see, I have a uniform density everywhere. When they pushed everybody out, it should look very much like what I had before, with the exception of the origin, right? The origin, I have to make room for this new orbital that's now going to be empty. But in the bulk, that density better be the same constant density as I had before. So this charge has to be sitting in the orbital that I had to make room for, and the size for that orbital is the magnetic land. So this charge has to be localized within a region of size magnetic land. Okay. Now this is one, that's argument number 1. This is the least precise because, see, I'm using here notion that it's a little county that I say, well, I have E per 3 orbitals, I take one orbital, so I'm going to take charge E over 3. Let's try to do better and better job.
I have a question. So, in case we are thinking in terms of its state, say in an annular disk or something, would that mean that you are creating like a positively charged excitation on the inner edge and negatively charged?
Exactly. If we had this geometry here, it's coordinate geometry. If I insert one flux quantum, the same thing should happen here, like we should push the orbitals away. So I'm pushing charge. I'm pushing all the orbitals this way. So what happens is that on this edge I will get plus E over 3, leaving behind minus E over 3.
Does that really happen?
You should see what will happen, yes.
Okay.
That's you think about as really moving charge plus E over 3 out. And, we get to talk about more about charges on the edge when we talk about experiments that actually detect this fractional charge. Okay, let me do now argument 2. So argument 2, remember when we were inserting this flux, Pierre said, okay, wow, you have to consider the Faraday force, right? The Faraday effect. As you insert the flux, you generate an electromotive force, but you have a system that has a Hall conductivity. So as you insert the flux in your system, you're going to generate a radial electric field And this, the line integral of the electric field E dl has to be equal to the derivative of the flux with respect to time. And well, there's a 1/c here. Let's put that one there. So we can figure out that the radius r, we have that the E in the theta direction times 2 pi r is equal to 1/c d phi dt. Now let's look at our relationship between the J and the E. Well, if E is pointing this way, J points this way. Right? Because the J in the R direction is going to be sigma, the sigma xy, the whole conductivity, so it's perpendicular, times the E theta. But now I'm not interested just in the current density. Let's say we took the circle of radius R. Let's integrate J over all theta times R d theta is the size of your segment here. That times JR. That should be equal to the current that's going out in through this circle of radius R. So this here is integral d theta of R times sigma xy times E theta. And we know what E theta is. So in particular, well, the angular integral just is 2 pi. 2 pi times R is this here, times E theta. This is equal to 1/c sigma xy times d phi dt. Okay, now this is the current. If I integrate the current over time, I get the charge that gets pushed out. That should be equal to sigma xy divided by c integral d phi dt and this is, at the end of the day, this is just the flux form that I inserted, right? So we have the charge that's pushed out is the whole conductivity times phi 0 divided by c. Phi 0 divided by c, it's hc over E divided by c, which is equal to h over E. So Q out is h over E, a ratio of fundamental constants, times the whole conductivity, which is quantized. So at this point, I want to stop to discuss this formula, because we just related the charge that gets pushed out to the conductivity. Now, you see next, when I calculate this charge, and I want to keep it in this form for now, to make an argument that fractional conductivity would imply, fractional Hall conductivity implies fractional charge. So these two things are hand in hand. This is actually one argument that Laughlin was very, hold on to it, saying that one didn't even need to go do experiments to prove fractional charge, because in itself, fractional Hall conductivity was already evidence for fractional charge. Well, to that I should add that if you don't see it, if it's there, there should be a way to probe it directly, because see, this is theory, okay, and it satisfies the constraint that it's so beautiful that you can say that it cannot be wrong. But still, there's the balance between truth and beauty, and it's only going to be true if you can see it. And by the way, wasn't it in Millikan's experiment, wasn't there some bad data points that actually had a charge less than E? Right? So there were some bad data points. That's not necessarily evidence for fractional charge. That's evidence for a bad data point. So you have to make sure that if you're going to devise an experiment and you're going to talk about that, it has to be proving what you think it's proving.
I have a question. Sigma XY, the quantized Hall conductance is a property of the ground state itself, right? You don't need to think about excitation. Isn't that true?
You don't have to think about excitation.
So this formula relates the excitation charge to like the ground state properties of Hall. So it seems it seems they are linked, which is not intuitive to me.
Well, I could argue that. See, I'm creating an excitation locally here, but I can draw this radius very far away. And you would expect that the Hall conductivity, even though I'm discussing an excited state, which I think might radius very far away, that all I'm using is a property of the ground state. It's with the notion that the Hall conductivity far away shouldn't care, shouldn't differ at all from the Hall conductivity of the system without doing applying any voltage, any flux. That's a good question. And the other thing, also you could ask the question, okay, how does, when you say the Hall conductivity is quantized, we're only talking about the ground state, but you can ask about temperature, right? What happens if, you always do an experiment at some finite temperature? The Hall conductivity should be quantized, there should be corrections. Well, these corrections should be exponential in the energy scale, the gap divided by temperature. So if you start doing experiments at temperatures which are comparable to the gap, you shouldn't expect the plateau to be too robust. You're actually going to start messing up the plateau. And by the way, we've heard a bit about quantum critical points. Let me make one comment here, that there are quantum critical points all over the place in the Hall effect, which is, well, as you change the magnetic field, for example, if you look at rho xy, for example, well, you have these steps, right? We talked about steps. Well, that's the idealized zero temperature curve. At finite temperature, well, you should start smearing the plateaus, but the region where it's most noticeable is between the plateaus, because you're having a transition between one state and the other. And if you look at rho x, it's also not going to be perfectly zero. It's going to have this peak. And by the way, this is why in the data there were some peaks, right? Because the data wasn't taken at zero temperature. These are two different phases corresponding to two different quantum Hall liquids. So you cannot go straight from one to the other as you change field. There has to be a phase transition. So there has to be a quantum critical point sitting somewhere here. And you would expect all the scalings that would come in with the quantum critical point, that as the temperature goes to zero, the width of this peak will go to zero, etc.
Question. How do we know it's continuous and not first order?
How do you know that it's continuous and not first order? That's a good question. Shankar, you thought about this problem?
I don't think it's easy to calculate the order of the phase transition. First principles. I mean, what's the order parameter that exists in this?
Well, but the scaling, perhaps scaling with the scaling of the width could tell you something, because if you have a second order transition, there should be scaling of the width of the peak. But now let me tell. I don't want to go too much into this, but let me tell. Well, wasn't there an experiment of scaling? There has been some experiments particularly by Dennis Shahar, where he goes down and down in temperature. He sees the scaling of the peak, but then at one point stops. Okay, And this has been a puzzle because first thing that theorists would tell him, well, your temperature is not what you think you are, right? You cool down and your thermometer is one thing, your electron gas is another. That's the typical theorist, like, yes, yeah, right. But still, last I heard, it's not very clear what's going on. So, and I would say that's one of the cleanest systems to actually put to the test ideas of scaling in concrete phenomena, right? And there we have this puzzle. This width should go to 0 at 0 temperature. It's not going to 0. Okay. Even if you had disorder, you would argue it has to go to 0, right? There are disorder, critical points with disorder. Okay, so I'll stop at that comment. But if things were ideal, then that scaling, if you went all the way down to 0, there could be some evidence at second order. Okay, so let me finish this one here. Now,
there was a question about the fact that the charge, the charge of the wheel is going to go out to the property of the charge state, but the conductivity is not. But the conductivity,
you have to be careful. Conductivity is actually also calculated as a, say, JJ correlation. It knows about yeah.
It's a limit as omega goes to 0. It's not omega equals to 0. It's never omega equals to 0.
Right, but you could say, okay, it does depend on the spec, because if you insert, let's say, in the Kugel formula, JJ, the ground state is sitting outside, but you need to insert something. You need the correlation functions of the current with the excited states, right? Yeah. But
I think there's also an energy denominator, JJ over omega or something, because E is derivative of the vector potential, and then you get factors of omega in there.
Yeah, well, it's there's a 1 over omega where you take 2 derivatives of vector potential. But if you have the gap, I would say that so it's the conductivity calculated with the ground state to actually carry. If you were to carry a calculation, you would need excited states to do just plug in a Kugel formula. Here you notice that we avoided any Kugel formula, right? We had more kind of the gauge argument. It's more powerful than that, right? It would be a nightmare to actually try to calculate it from Kugel formula. You might do it if you have a simple argument. And in that case, we just did everything at 0 temperature. Right? You just use that adiabatic theorem. Okay, let me finish this one here. It's HE over the times sigma xy, which is HE nu e squared over h. The h cancels, one of the e cancels, and you get nu e. So the same nu of the filling fraction is your charge that's being pushed out in this argument. So that bypasses this issue that we did this cheesing counting, say, okay, it's 1 electron per 3 orbitals, we keep 1 orbital. That's more precise, right? The final one, I'm going to do it because later on we're going to need something like this to talk about statistics. Okay. So this argument is actually due to Arovas, Schrieffer, and Wilczek when they showed that quasi-particles also have fractional statistics. But one step, the first step is actually ask a similar question where instead of putting 2 of these quasi-holes, you have 1, and with 1 you can figure out the charge. Yes.
Is the Laughlin crystal in this phase diagram?
Is there a
Laughlin crystal?
Oh, at much higher fields, yes. See, there's a question of energetics, right? Because so suppose that you diagonalize. This is a way to think about it. Suppose you diagonalize the system where you keep on changing the filling fraction. Whether you're going to have a Laughlin liquid or a Wigner crystal actually depends on the details of the energetics. That for nu equals 1/3, 1/5, you have a good the Laughlin state wins, has a lower energy. But when the filling fraction is very, very dilute, so I forgot exactly if it's around 1/9, but at those very low densities, the Wigner crystal would win. Okay, I have 10 minutes. I'm gonna try to rush a bit through this argument so I can have some time to talk about ways to measure fractional charge. So let's take that wave function again. Let me rewrite it. Let me call this plus Z0, where I've got a quasi-hole at Z0, and the wave function depends on the position of the electrons. Times now let me put a quasi-hole at Z0. Actually, let me allow this position of the quasi-hole to move, because I want to move it around. And now, you can think about this as this is just a label. Your wave function depends on the position of the electrons. It's not a wave function of the quasi-hole. The quasi-hole is a point where you put a hole there, right? You put something there, and you can actually move this guy around, and you get different wave functions. So the wave function is the wave function of electrons. If we put this hole here and take it for a walk around a certain area, well, there's magnetic field here. There's magnetic field through the whole plane. So if I take this guy for a ride, at the end of the day, when I come back, I should have picked up a AB phase, an Aronoff-Bohm phase. And this Aronoff-Bohm phase is going to be E star divided by H bar C times the integral of dl dot A, where A is the vector potential. Oops. Okay, and this is just the flux, and I can write this whole thing as see, this is related to the flux, and I can write this as 2 pi. So the AB phase should be right with E star over E times the flux divided by phi 0. The flux around the area here. If I had put an E here, that would be the end of the story. It just depends on the flux divided by the number of flux quantum there in the circuit. But I'm allowing for an E star here. And I haven't said what this E star is yet. Okay, that's one way to talk about this phase. Now I can calculate this phase without mentioning Aronoff-Bohm effects, because see, I have the whole wave function, and I could ask, okay, what is the phase that I pick by moving this guy very slowly around and coming back? Okay, this is one problem where we can talk about a Berry phase. That's exactly what the Berry phase does, right? So suppose that if you want to really think about the Hamiltonian, suppose that I come in with some kind of STM tip, make my little hole, quasi-hole, and I move my tip around. Okay, that's a theorist experiment, right? Of course. But you move your quasi-hole around, and I come back. At the end of the day, my tip is on the same place, the Hamiltonian is the same, but I took my hole for a ride. So I adiabatically change my Hamiltonian. We can calculate some adiabatic phase. So let's calculate the Berry phase. Okay, let me ask something. Who has heard about Berry phases here? Okay. And so here we're going to do a simple calculation of a Berry phase. I'm just going to use the result of Berry, what that phase is. And that phase should be exactly the same phase that's picked up here. Okay, so No, it's no big deal. It's actually something very simple. I really suggest that you go read the original paper by Barry. It's beautiful. All you need to know is quantum mechanics. And it's a beautiful, simple paper. So it's one of the must read. Even I can understand it, okay? So the phase, the Barry phase is this, is that we can calculate when you take your state for a ride between some initial and final time, such a way that it's a closed path, and your Hamilton comes back to the same place. And you calculate the phase picked up by, you just calculate the overlap of your wave function with the derivative of that wave function with respect to time. Now I'm going to plug in this wave function here. So let me calculate what is the y3 plus z0. Y3 plus z0 overlap with the derivative with respect to time of y3 plus z0. The only thing that depends on time here is the z0. These z's here are going to be integrated over. When I calculate the overlap, they're just integrals. dz1, over the plane, d2, z2, z, etc. So this is the only thing that depends on time. So you take the derivative, I have this product. Every time that I take so I have a derivative of a product, I'm going to get a bunch of terms, and then for the given I in that expansion, when I take the derivative, I'm going to pull a minus z dot. Okay? This on the side here. So I have z1 minus, let me do for 2. If I take the derivative of this one, in respect to time, you get minus z0 dot times z2 minus z0 minus z0 dot times z1 minus z0. And I can write this as minus z0. I get some of two terms. This one I'm missing my z1 minus z0 that I had before. So let me put it back. So let me write this as z1 minus z0, z2 minus z0 times minus z0 dot divided by z1 minus z0 plus minus z0 dot z2 minus z0. And this here you can even write as ddt of the log of z1 minus z0. Same thing for the other one. And I have a sum of terms. So here, I'm going to have, and this factor that I pulled out is just the one that I had before. So I can, this is just going to be our wave function as before, but we're going to have the sum over I of ddt of log of zi minus z0 of t times the wave function psi 3 plus z0. Well, I don't like doing sums. It's hard, so let me rewrite this as an integral over the density operator, because the density will pick up this it's delta of r minus the position of the particle. Then I don't have to do the sum. I can just do the ddt of log z minus z0 of t and this guy is a bunch of delta functions that I'm going to pick up my position. So now it's easier to do those integrals because this derivative here, this term here, looks like minus z0 dot divided by z0 minus Z. Now let me do this integral over time now. See, this is just a number. I can just pull it out. And then I have to calculate this overlap. So I have this Z0 dot divided by Z0 minus Z. Then I have the overlap with the density operator. So that's nice because it's just going to give us the expectation right after density. And I have the end to do the spatial integral. This integral here is the integral of dz0 divided by z0 minus z. As I move around my quasi-hole. Well, that integral. So if z is inside the path, I pick up a 2 pi I. If the z is outside the path, I pick 0. So this guy here is equal to 2 pi I if z is inside the path, and 0 otherwise. So I get that my gamma is 2 pi I times I is minus a 2 pi. Then I can do this integral over the density, because, see, I only pick up the contributions when R or Z, two different ways of thinking about the same thing, is inside the path. If R is outside, I pick no contribution. If R is inside, I pick a contribution. So this is just the average density of particles times the area in the path, within the path. Now the number of particles, remember the filling fraction is nu, so the number of particles is just nu times the density of flux tubes. So this is equal to nu times, and if I multiply the density of flux tubes times the area, I get the total number of flux tubes. But that one is simple. It's just the flux in the area divided by the number of flux quanta. So let me carry this over to the other side. We're almost done.
How do you get divided itself? Divided itself.
I know. But I'm going to be 2 minutes over on top of the 5. Okay, so let's copy this over. Gamma is equal to minus 2 pi nu times phi divided by phi 0. And that's the final answer that they have to compare with this guy here. So if I set these two phases the same, well, 2 pi's cancel, and I get that minus nu is equal to E star divided by E, or E star is equal to minus nu E. And amazingly, even the sign we got it right. Okay? So that's the third argument. So this particle that you took around, and you can calculate the phase by just Barry's argument, by adiabatically moving this guy around without resorting to the Aronoff-Bohm effect. And then you match the two. You say, okay, this phase is exactly the Aronoff-Bohm effect, that a charge with, say, 1/3 E, minus 1/3 E, would see. All right. So here we stop all our arguments about fractional charge. Next time, since I ran out of time, I'm going to talk about a couple of experiments that detect fractional charge. There's actually two experiments in '97 in Sinclair and in Wiseman, and some more recent experiment by Jacobi that show you that actually this thing is real. You can see. And then we talk about fractional statistics. All right. So enjoy. Nobody asks questions, so I can keep the schedule.
Okay, so thank you.
Questions you leave for Friday. You come in with your questions. Okay? All right.